Okay, we are in live. Hi everyone. Today's seminar will be about prime numbers, number theory, and some related studies, related topics. And our speaker is today Mohammad Sadek, who is the associate professor at Sabanci University, Mathematics Department. And he received his bachelor, University of Cairo, and then he received a PhD from University of Cambridge. And his research, he focused on some computational number theoretical question, arithmetic geometry, and elliptic curves. And that's it now. Okay, we can start actually, if you wish.
Thank you very much.
There is a question in chat. I will inform you, Hocam.
All right, that's quick.
There's no any question in chat now. And then maybe at the end of the seminar, if you wish, we can.
Sure.
Okay.
Sure. Thank you very much for the introduction, Rusto. I'm happy to be your guest. I know it's quite late now, so I'll try to be quick. I'll go easy on you. Right, so let me see if I can share my screen. Can you allow me to share my screen, please?
You can share now, Hocam.
All right. So you see it full screen, right? Right, so let me start with telling you why I chose to talk about primes today. You are meeting someone for the first time, you want to have a friendly conversation. You start with exchanging smiles and names, and then comes the part when you are telling what you do for a living. I'm a mathematician, and this kills many conversations for me before. However, usually I'm trying to be friendly. I want to keep the conversation going. So I'm like, hang on, yes, I'm a mathematician, but that essentially means that I'm interested in patterns. I love patterns, I hunt for patterns, and I study patterns. And being a prime integer, that's a pattern that have been occupying mathematicians for thousands of years. So before kicking off, of course, I need to remind you what a prime is. And I cannot find a better way to recall what a prime is than mentioning something about Don Quixote. You probably know about this novel. Don Quixote is a Spanish novel by Miguel de Cervantes, and it was published in two parts, 1605 and 1615. And it's considered as a founding work of Western literature. It's considered as the first modern novel. It's labeled as one of the greatest works ever written, and it's known to be the most translated book ever as well. Right, so it's big. And the main character obviously is Don Quixote, who is in love with some peasant lady, Dulcinea del Toboso. And then in one scene of this novel, there is another character, and this character is called the Bachelor. And Don Quixote is begging the Bachelor to write a poem on behalf of him to describe how much he loves this lady, Dulcinea. So that's good. Obviously, he loved her very much, but it's cheesy, right? I mean, many people are doing that, especially back then. But he asked for more. Not only he asked for a poem, but he asked for a poem which consists of lines where each line starts with the letter of her name. So when she puts together all the letters, all the first letters, she reads her name. So that's slightly more than writing a poem. Right, but then the Bachelor figured out that there would be a problem. In fact, he figured out that the task would be impossible to achieve. And the reason is Spanish poetry itself. In order to write a Spanish poem, you don't only write verses, you don't only write lines, but you have to write your poem into groups called stanzas. And the stanza is of fixed length. It's either of length 4 lines throughout or of length 5 throughout. So the bachelor is telling Don Quixote the following: I tried, but it seems impossible. Because whenever I try to write stanzas groups of size 4, I write 1 stanza, 2, 3, 4, but 1 letter is left out. And if I try the other length, 5, I have 1 stanza, 2 stanza, 3 stanza, and 2 letters will be left out. And the problem was basically that Dulcinea del Toboso, her name consists of 17 letters. And in order to write a Spanish poem, the length of it should be a multiple of 4 or 5. So in order to achieve the task of Don Quixote, you have to change the whole structure of the Spanish poem. You have to allow stanzas of length 1, which is very short, or 17, which is very long. So yeah, Don Quixote, he should have counted, but at least we know what the definition of a prime is. You can think of a prime as a poem, a Spanish poem, in which the allowed stanzas are only 2, stanzas of length 1 or stanzas of length the poem itself. Basically, a prime is an integer which is a double, so which is a multiple of exactly 2 integers, 1 and the integer itself. Right, so we know what the definition is. Now let's start with telling what the first few primes are. So the first few primes are these. And don't worry, I'm not mixing up my fantasy team for the Premier League with the slides. These are some fine players, all right. And that's a not bad team, but all you need to do is to ask them to turn around to read the numbers on the back of their t-shirts. So these are the first 11 primes. Well, I have to say something. I wasn't happy with number 13 as the goalkeeper of Crystal Palace, and Crystal Palace is not doing that well, really. But I didn't find anyone that I like wearing 13, so that's it. And then you convince the middle school students and even primary school students that prime numbers are important simply because any integer can be written as a product of these primes. So once you know what the primes are, any other integer which is not a prime is just a product of these primes. That's called the fundamental theorem of arithmetic, and even a Messi can be written as a product of some primes, right? Messi is wearing now a very funny number, 30, but 30 is nothing but a Kyle times a Fabinho times a Jorginho. So 2 times 3 times 5, and nothing special about Messi. You can replace Messi with any integer. And the fundamental theorem of arithmetic would work nicely. Right, so we mentioned the first few primes. Now, what's next? What's next is to tell this sequence of primes, how far it can go. How many primes are there? And this question, although it might look hard, but it was answered more than 2,000 years ago by Euclid. And the statement of the theory of Euclid was, even if you manage to convince every single player in the Premier League to have a prime printed out on the back of his t-shirt, you will never, ever have enough players. Well, his statement was slightly more precise than that. He said that there are infinitely many primes. So there are infinitely many primes, and the proof is quite beautiful. In fact, the proof is one of the first proof in history using contradiction, but I'm not going to rewrite the proof now. Right, so we know what the primes are. We know that there are infinitely many. We have the fundamental theorem of arithmetic. Now let's go to the questions, the question that I want to discuss with you today. If you write down every single integer and you start coloring the primes with a different color, and you are trying to find a pattern in these primes, there is no way you can expect when the next prime is coming. The question is, these primes look random. They are scattered throughout the integers. So how can we measure this randomness? Is there a way to measure this randomness? Paul Erdős, a very famous mathematician, and that's one of the rare pictures where he's smiling. Yes, he's smiling. Had an opinion about it. Remember when Einstein was telling that God is not playing dice with the universe? So Paul Erdős agrees, God may not play dice with the universe, but definitely God was playing dice with primes. They are random, they are absolutely random. And the question is, although they are random, there is chaos, how can we find the order in this chaos situation? Right, so a fine mathematician, German mathematician, Gauss, he is the guy printed on the old 10 banknote, the German one, the mark. He came up with this idea. What if I give a measure for this randomness? So I know that there are 4 primes between 1 and 10. I have 2, 3, 5, and 7. You can do the same up to 100. Count the primes. There are 25 primes. Up to 1,000, I have 168 primes. What Gauss suggested was, okay, today I finished counting all the primes up to 1,000. Tomorrow I'm going to count all the primes from 1,000 up to 2,000. Then let's count the primes from 2,000 to 3,000 and so on. And let's observe the behavior of the frequency of the appearance of the primes. Gauss in 1792 managed to do so up to 3 million. So, for example, when you are between 1 million and 1 and 1 million and 100, these are the only primes. There are 6 primes. So one of his observations was, as long as I'm counting more and more, the frequency of appearance of the primes is getting less and less. So he came up with a counting function. So this counting function is nothing but a counter which adds 1 whenever you are meeting a prime. So for example, pi 10, that's the number of primes up to 10, that's 4, we already saw that. Pi 100, that's the number of the primes up to 125. By 1000, that's 168. And then he constructed a table. His table was more complicated than that. However, basically that was the idea. In the very first column, this column, he has the bound. In the second column, he has the pi x, the counting function. And then in the third column, we'll have the ratio. So as you see, the observations are, if you look at these ratios, the ratios are getting really less and less. As long as this x is getting larger and larger, the bound is getting larger and larger, the primes are getting fewer and fewer. Not only this, if you look at 10 squared and 10 to the power 4, 10 to the power 4 is the square of 100, the ratio of the primes is 1/4, 0.25, when the bound is 100. However, it is almost half of this when the bound is the square of 100. And that's not a coincidence. If you go from 10 to the power 4 to 10 to the power 8, which is the square of 10 to the power 4, and you observe the corresponding ratios, almost the same behavior. I'm halving. So from calculus, you know that there is a function that acts similarly. There is a function when you raise to the power 2, the value will be doubled. The logarithmic function, right? The logarithmic function, it takes the power down. But here I'm not doubling, I'm halving. So pi x over x, the ratio of the primes, it acts similarly to a function that we know, 1 over the logarithmic function. So that's what Gauss was trying to do. He drew 2 curves, one corresponding to the counting function, one corresponding to x over ln x, and his observation was not only that these curves are very close to each other, but as long as you are going deeper and deeper to the right, these curves will get closer and closer. Gauss was not trying to find a closed formula for the counting function. Gauss was trying to study the behavior of the counting function. He was trying to look for a function that acts in a similar way to the counting function. So in 1792, he had a conjecture that the ratio of the primes acts similarly to 1 over ln x, 1 over the logarithmic function. They are not the same, but they are acting similarly. This means that the difference in between is very small. Right, by the way, this conjecture was in 1792. Gauss was born in 1777. So when he did this act of counting primes up to 3 million and coming up with this conjecture, he was 15. Yes, because this is what you do when you are 15 and bored. Right, but this conjecture had to wait for 100 years to be proved. And it was proved by 2 other mathematicians, and now we have a big name for it, the prime number theorem. They managed to prove that the conjecture of Gauss was indeed correct, that pi x and x over ln x, they are indeed acting the same way. When you take the limit, then these 2 functions, although they are not the same, but they can get as close as I want. Right, so roughly speaking, if you don't like limits, if you don't like your calculus 1 and calculus 2, so let me tell you what this means really. So pi x over x and 1 over ln x, they are acting the same. This was a conjecture, and now it's the prime number theorem. That's the ratio of the primes up to the bound number x. So this means basically that the probability that a certain number is prime is 1 over ln n. Let me simplify it even more. Have you ever considered whether your phone number is prime or not? You definitely didn't. Okay, I did. However, my number is quite annoying. It has this 0 by the end, so this means that it's divisible by 10. However, when you divide by this 10, you are left with a prime. So let me tell you what are the odds that your phone number is prime, but please try it after we finish. A Turkish phone number, it consists of 10 digits. So according to the line that I have here, the probability that your phone number is prime is around 1 over ln of 10 to the power 10, which is 1 over 23. Roughly speaking, that means that about 1 in every 23 Turkish phone numbers is prime. So there is a high chance that your phone number is indeed prime. Right. So what's next? Let's do more. Let's not ask about only trying to find the order and the chaos, but let's do more. In calculus, you studied sequences. You have a sequence, you have a first term, a second term, a third term, and then you are looking for the general term. So for example, the sequence of squares, 1, 4, 9, 25, you have a general term for this, n squared. So when you replace n with 1, you will get the first term. When you replace n with 5, you get the fifth term, and so on. Let's try doing the same with primes. Let's order the primes. So I have a first prime, which is 2, a second prime, 3, a third prime, 5, and so on. That's a sequence. The question is, can I find a general form for it? Can I find a machine for which the input is the number of the elements and the output is the prime whose order is this number? So that's another big question. How can I produce the prime number n? Is there a general form to produce this prime or not? Right, so instead of considering that specific question, I'm going to consider 2 simpler questions. The first question is, can you think of a polynomial that takes infinitely many prime values, which means that I have infinitely many inputs. When I evaluate my function at these inputs, the output will be a prime. A harder question. Can I find a polynomial which only takes prime values? So no matter which n you are going to choose, when I apply my polynomial to this n, I'll get a prime on the other side. So these are the 2 questions that I'm going to talk about now. So a polynomial, is it possible that I can find a polynomial that takes infinitely many prime values? Another fine mathematician, Dirichlet, he told us that the answer is yes. Think about the polynomial 8n plus 1, a very simple polynomial, a polynomial of degree 1. If you look at some values, you'll see that when you evaluate this polynomial at 2, you'll get 17, a prime. When you evaluate it at 5, 8 times 5 plus 1, that's 41, it's a prime. If at 6, 47, it's still prime. If at 500, that's 4001, still a prime. But he didn't only observe that there are many values are prime, he managed to show that, in fact, 8n plus 1 assumes infinitely many prime values. Same for 15n plus 7. These are some prime values. He managed to show that for this linear polynomial, for this polynomial of degree 1, this polynomial assumes prime values infinitely many times. Nothing special about 8 and 1, nothing special about 15 and 7. Dirichlet managed to prove in general that if you have a polynomial of degree 1, a polynomial of the form an plus b, then this polynomial will take infinitely many prime values. The only condition, the only technical condition is this a and b are relatively prime. There are no common divisors, because otherwise you will take this common divisor and you will not have a prime. So for linear polynomials, obviously Dirichlet, around 200 years ago, managed to show that any linear polynomial satisfying a very simple technical condition will assume infinitely many prime values. But what about polynomials of degree at least 2? The simplest that I can think of is n squared plus 1. Of course, not n squared, because n squared it will give you squares. So when you evaluate f at 1 is 2, f at 2 is 5, f at 4 that's 17. So I can produce as many prime values as I want. Unfortunately, we have a conjecture, something that we believe is true, but we don't have a proof for it. If you have a polynomial of degree at least 2, plus other technical conditions, then this polynomial must assume infinitely many prime values. That's a conjecture. Not only this, the case is worse than that. This conjecture hasn't been proved for a single polynomial, not even n squared plus 1. So n squared plus 1, we believe that it assumes infinitely many prime values, but we don't have a proof. Right, so let's move to the next question. The next question was, can I produce a polynomial that takes only prime values? So not only infinitely many, but every single value that will be taken by a polynomial, it should be prime. Another fine mathematician, Euler, a Swiss mathematician. Again, he's the guy on one of these 10 banknotes. I'm not sure what's wrong with 10, but yeah, mathematicians, they are put on 10s. Mathematicians used to call him the master of Asul. He was something, he was a big head. He came up with this example, a polynomial of degree 2, n squared plus n plus 41. When you evaluate f at 0, you'll have 0 is plus 41, that's 41, prime. When you evaluate it at 1, you will have 43, which is another prime. F at 2, 47, a prime. If you keep evaluating f at every single positive integer up to 40, you are getting a prime. Okay, so he's right on track. Remember, we're trying to produce a polynomial which, when you evaluate at every single n, you'll obtain a prime. So the first 40 values, when you evaluate f at these integers, you will get a prime. However, f evaluated at 41 is not. And the reason is very obvious. When you put 41 here and 41 here, because the constant term is 41, obviously you can take 41 as a common factor and you will not have a prime. Nothing special about this polynomial. If you take any polynomial of any degree and you evaluate it at the constant term, then the constant term will appear in every single term, and then you can take it as a common factor. So the answer of Euler to this question was, it's impossible to construct a polynomial in one variable that takes only prime values. And the reason is very simple. Think about the constant term. Right, but maybe we're looking for the wrong polynomials. We're just considering polynomials of one variable. Maybe you have to consider polynomials in more than one variable. Matiasevich in 1971 and some other guys managed to answer this question positively. In fact, they came up with a polynomial in several variables, 26 variables. That's very convenient because that's the number of the alphabets. So you can call all your variables A, B, C up to Z. Right. However, the polynomial is a monster. It's a polynomial of degree 20 and 26 variables. So what about this polynomial? If you choose numbers A, B up to Z, such that the value of this polynomial is positive, then this value, it should be a prime. Not only this, if you think about any prime, I can find the corresponding A, B up to Z such that when I plug in F, I'll obtain that prime. It's a nice piece of mathematics, useful, might not be. Right. So by now, you're probably saying, Hojam, we are happy that you are a happy mathematician, but why should we bother? What can we do with these primes? The fact that you are sitting in front of your YouTube channel right now, watching this stream, means that you are using a prime right now, at the very moment. If you look at the address bar, this lock that you have in front of you means that there is a prime in action. Yeah, I'm sorry about these videos the kids were watching. Right, so before talking more about these primes, let me tell you something. Without primes, life would have been completely different. Forget about online banking. You'd have to go to the bank, do whatever you want to do there in person. Forget about online purchasing. You'll be carrying cash all the time. Forget about WhatsApping. Forget about emailing. It would be pen pal by now. Right, so why primes? Why do we use primes when it comes to internet security, banking security? It's because of this randomness that we cannot predict them. It's because the methods that we have to test a single integer to be a prime or not, they are very slow. Before talking more about internet security, I need to introduce two technical terms, encryption and decryption. So whenever we're talking about security, there is some kind of information that I want to hide, that's encryption, and then I want to decrypt. So this means that I want to recover the information. So hide because I want some people not to see my information, and recover because I want a certain person to see my information. Encryption and decryption, where are they being used? Internet, computers, smartphones, smart fridges, anything smart around you. Encryption and decryption, meaning primes. Right, so I'm going to present one of the famous ways of securing information, but firstly, I'm going to introduce the physical problem, show you where the question is, and then I'm going to introduce a physical solution, and then the next question will be how to model this physical problem and its physical solution. So a piece of my artistic work, there are two guys, Olive and Burke. Usually they are Alice and Bob, but for now, Olive and Burke. So Olive has a message, and she wants to send it to Burke. There is a problem. They're completely strangers. They haven't met before. However, they want to share a secret, and the only way they can share the secret is through an open channel and secure network. So this means that there are eavesdroppers, there are people watching, there are people actually that can see what you are sending. So the question is, the physical question is, how can I share a secret through an open network where people are watching what I'm sending? That's a difficult question. I'm sending a secret, but everyone is watching. How would that be a secret? Right, so that's a physical problem. So let me introduce the physical solution, and then we'll talk about the math. The physical solution is as follows. Lock and key. They're going to play a lock and key game. How would it work? Simple. Olive, she's going to put a lock on her message with a key that she only has. And then she's going to send the message to Burke. Everyone on the internet sees a locked message. Nobody has a key, including Burke. And so they cannot open the lock. They cannot see what's inside the message. Now Burke, he doesn't have a key, but he's going to have another lock. Lock it with a key that he only has. And then you would stop and tell yourself, these people are quite weird. There is something definitely wrong about Olive and Burke. They don't know how to share a secret. That's not how you share a secret. But the story doesn't stop here. Burke is going to send the double locked message to Olive. Olive has the red key. Everyone sees the double lock, but Olive is the only one who has the red key. Unlock it. You know what's next, of course. Send it back to Burke. Now there is only one log that needs a green key, and only Burke has it. Unlike it, Burke is the happiest person now, right? So that's the physical problem. And the physical solution, obviously very simple. The question is, how can we use math to model what you had in front of you? This is how we use math. I'm going to introduce الجمل public key crypto system. Again, you know why public? Because everyone is watching. Everyone can see what you are sending. The question is how to hide your information. So what's public? What's every single person know is a prime P and an integer G. And as usual, we have Aleph and Burke. Aleph has a message. This message is a number. It might be a bank account number. It might be a credit card number. Aleph and Burke, they have their own keys and they start producing their locks. They take this G, they raise it to the power A, and Burke is going to raise this G to the power B. So we have two locks now. Now Aleph is going to use this double lock to hide the message. How do you hide the message? You are multiplying M times a double lock, B to the power A. Remember, B has small b on it, and now it has E on it. So that's the double lock. And then she's going to send it through the open channels, through the open network. So it's public. Everyone sees the hidden message, but they don't know what the message is. It reaches Burke. Burke has the key. And that's how he recovers his message. He multiplies e to the power negative b times the hidden message. That's what you get. I'm just replacing a with its value. I'm replacing m with its value. And that's what you get. So you have some powers. And these powers can be simplified. And luckily, when you add these powers, you will get a 0. And so Burke managed to recover his message. So only Aleph and Burke managed to share this secret. Public, they only saw this capital M here. Okay, right. So that's the mathematical solution to the problem. This is how we can use prime numbers in internet security to cover a certain message. Right, before I finish, I have like 10 minutes. So let me walk you through a journey. What's the largest known prime right now? Right, there is a strategy to find large prime numbers. And this strategy is as follows. You consider a certain sequence called Mersenne numbers. If you are taking an elementary number theory course, then you probably know about these Mersenne numbers. They are very simple number in structure. They are a power of 2, but you are subtracting 1. If you want to see the first few of them, that's the very first Mersenne number, it's 1. The second is 3, you have 7, you have 15, the fifth, 31, and so on. Even in elementary number theory course, we know lots of things about these integers. I know that if it happens that one of these numbers is a prime, look at 31 here, then the corresponding index, it should be a prime as well. It's not the other way around. So I might have an index being a prime, but the corresponding Mersenne number is not a prime. Think about M11. So the strategy is the following. You look for primes in the sequence 2 to the power p minus 1, where p is prime. Why do we like Mersenne numbers? Why Mersenne numbers are the numbers to consider when we are looking for larger primes? Because we know lots of things about them. We know how the factors look like if they're not primes, for example. We have simple tests that tell you whether a given Mersenne number is prime or not. A test that works faster for these integers, but not for any other integers. Right, so let me tell you the largest known primes. Euler was the first to deal with these large primes. In fact, he managed to show that 2 to the power 31 minus 1, which is a number slightly bigger than 2 billion, is prime. And then a guy called Lucas managed to show that 2 to the power 127 minus 1, which is a number consisting of 39 digits, is prime. I like these records more than any others because the only things these people were equipped with, a paper, a pen, and a brain. There were no computers. Now, let me show you the largest known primes decade by decade, starting from 1952. That's a prime. That was the largest known prime in 1952, 2 to the power of 521. You see the jump between this power and this power. Then in 1961, that was the largest known prime, another Mersenne number. So we are going up from few hundreds to 4,000, almost 4,500. In 1971, we are going from almost 5 to almost 20,000. In 1985, we are going from 20,000 to slightly more than 200,000. In 1996, not thousands anymore, we have millions, 1 million and almost 400,000. In 2008, that was the record back then, the largest known prime was 2 to the power, this power right here, which is slightly more than 37 million. And that's the current record. It's a number that was found in 2018, and now you can see that the power is 82 million and more. Right, so if you look at these lines, this reflects how our computers have become faster and powerful with time. This number that you have in front of you, it consists of 24 million and some thousands, almost 25 millions. You need thousands of pages just to write this number down. And it wasn't a one-man act. It was found through a project called the Great Internet Mersenne Prime Search, where small computers all over the world are connected through a network and people are just looking for these primes. So you are combining all the forces around the world of these small computers to have huge power to find these primes. These lines in front of you, not only they tell you how your computers have become powerful, but it tells you something about the power of the human mind. That might not express well how this number is large. Yes, it consists of 25 million digits, but there are people out there who are estimating everything around us. If you want to estimate the amount of sand in our planet, the estimate is 2 to the power 72. Look at this power now. If you want to find an estimate for the number of atoms in the universe, this is around 2 to the power 300. Look at this number now again. These lines, these records in front of you, not only they reflect how computers become faster, how computers became powerful, they reflect how curious the human being can be. We believe that these Mersenne primes are out there. We went there and we found them. Before I finish, let me ask you a simpler question. What's the largest prime number that appeared in a popular song? You might think it's 2, 3, 5. It's 867539. That's the hit in 1982. The song is called Jenny. That's a record easy to break. Thank you, guys. It was fun.
That's a great finish, Professor. We convey our thanks to you for your presentation.
Thank you, guys, for having me.
And also, and especially at the beginning of the seminar, is overlapped our studies, what we do in Reading Club.
Good.
That's why I wish get together again.
Thank you very much. Thank you, Rushta. Thank you very much.
There is no any question in chat, hocam.
All right.
I have a question
Maybe
actually,
we
Artis.
Do
May
you
I
have a
ask?
question, Taha?
Yes, I have one.
Okay, okay. And then maybe I ask something. Okay, go.
My question is, when we calculate the counter divided by, actually when we calculate the ratio of the primes, we take limit to the infinity.
Yes.
But there is the p function. Actually, we don't know anything about this function, even any rule, and how can we think about it, what it is going to do at the infinity?
Right. So remember when we talked about this randomness, we're not trying to find a closed form for pi x because it's almost impossible to find a closed form. And that's what Gauss suggested. Instead of looking for a closed form, let's look for a function that acts similarly. Acts similarly in the sense that when you take the limit, when x goes to infinity of the quotient, you'll get 1. So we have to go back to calculus 1 and remind ourselves what we mean by the limit. The limit of the quotient being 1, this means that as long as x is getting larger and larger, then I can make this quotient very close to 1. Not 1, but very close to 1, as close as I want. Right? So we're not looking for a closed form, but we're looking for a function that acts similarly. So as I said, pi x over x and 1 over ln x, they're not the same. They're just behaving the same way.
Okay, thanks.
Is it numerical methods or is there an analytic approach on this question? What Taha asked.
Pi x.
Yes, because we have distribution of primes and
Yes.
then take a limit and then we obtain the 1. But
Sure.
Actually, there is a better way to understand the behavior of the primes. So in your reading club, if you're reading about the Riemann zeta function, and that was the approach suggested by Riemann. So if you want to study primes better, then you have to consider other tools. And the other tools, the most famous tool is the Riemann zeta function, how to use the Riemann zeta function to understand more about the distribution of the primes.
Okay, if I remember correctly, it's an analytic approach.
It is, definitely, it is. Mostly it is analytic, but of course, there are algebraic takes on it as well.
Oh, okay. There's no another question, hocam. Then we can finish.
All right. Okay.
Thank you.
Thank you very much, guys. Thank you. Thank you for having me. Take care.
See you.
I'll see you. Bye.